So in this extended demonstration video number 5 in the course Bioimage Analysis, we'll look at fly embryo cell divisions over time. So looking at a series of images that I took a video of time-lapse images over time, looking at fluorescence of different cells and looking at tracking the movements of these cells over time that are deciphered as spots that are of interest. So we're looking at the fluorescence density as the form of coefficients of variation, and those are the standard deviations divided by the mean for each spot. And what we're looking at is thinking about the changes in the intensities over time across the different spots. We're really thinking about a kind of 4D model in essence here. So what we'll do first is install a bunch of libraries using this code created initially by Marion Laveau. And we have these packages that we're going to install that are mentioned at the top of the course. So let's move to our RMD file to do that now. So let's just check that those packages are installed now. So we can see that they appear to be installing okay. What we're going to read in is this file containing a CSV file of our time-lapse divisions for each of the spots. And we're just going to ensure that we have the correct path. We're going to use the read.csv _CSV function from the reader to read in the CSV file. And we're going to create tuples out of them. Tuple is like a data frame. So let's read that in now and then use the head command, pipe it to head to check what's inside. So we're checking the top of the file. And what we see there is that we're looking at 6 entries. They have first 6 rows by 22 columns. And those columns include the ID, the track ID, the quality, position, X, Y, Z, and T over time. So 4D. And then there's other ones like frame, radius, visibility, cell division time, manual color, mean intensity, median intensity, minimum intensity, maximum intensity, total intensity, standard deviation, estimated diameter, contrast, and SNR. So there's quite a lot of information in there that you can examine. We look at the structure of this as well. So we can see when we look at the structure, we have 11.3 thousand rows contain those variables we just mentioned. You note also that certain items are integers, characters, or doubles. So a double is a form of number as well. So what we're going to look at our coefficient of variations, and to compute that, what we're going to do is mutate to create a new column where we're setting the CV to be equal to the standard deviation column. So we're looking at the DF equals DF fly spots data frame, and we're looking at the standard deviation divided by the mean intensity there. So we look at this, we're selecting from that and getting these things, and then we're piping it to head just these 3 columns to check that it worked. So we're going to check that column is still there. So you can see a CV has been calculated from the mean intensity. So all those values are there, and the standard deviation. If you look at fly spots, we can also look at a histogram just to check the mean intensity. So you can see that those distributions there, there's not much variation. If we look at the standard deviation, again, you see it's quite bimodal. And then if we look then at other things inside there, such as the contrast, you can see again it's bimodal too. So what we're going to do is select the columns that we want to select for using the select function. So selecting the label, the mean intensity and standard deviation, and looking at the head there. So let's see what's in the head. So we have the label, the mean intensity and the standard deviation. We want to select just a few key columns and report them. So we're using the cable function from the knitter library to achieve that. So we're selecting these ones and just reporting them as a table. We're taking the head only and knittering this as a table. So we can see there a short table containing the mean intensities and standard deviation. If we remove the head command from the previous function, so just get rid of this, we get the full table, which is going to be quite a lot of data there, you can see. But you see certainly all the intensities around 32,900 or 700 and something. Okay, so what we're going to do is take ggplot and take in that data, and we're going to add on plot the mean intensity on the x-axis. So we're just looking at the frequencies of the different mean intensities. And we're going to create a histogram out of that with 15 bins. If we change the number of bins, it doesn't really change what we see. It just means that it's more specified. So we see there's some values that are low and most values are high. So what we can do is look at our value, the mean intensity over time, which is in the column of frame. It's a character, so we have to convert it to a numeric. So use the as numeric function to do that. And we're going to create a column called frame num containing the frame variable as a numeric data. So what we're going to do is pipe this into ggplot. So we mutate it to create the frame num column and pipe it into ggplot. So plotting frame num on the x-axis versus frame on the y-axis. And then we're going to use g_on_point to add points onto that. So that's what I'm doing now. So you just see that it's pretty much a linear correlation as you'd expect. So it's just frame versus its own values. If you add a smoother onto that, that just creates a line too. So there's no evidence of variation over time. So what we can do is filter the points a bit to get the filtered data set containing the points that have a mean intensity that are higher than this threshold. So if we go back to our intensity histograms here, you can see that there's some that are below this kind of threshold of 3 to 900. Now what we can do is just relax this a bit and see what we get here. We're going to filter that and then mutate it with the frame num there and look at the structure of that new matrix. So now we have 10,000 values and 23 columns. Our new columns is frame num. So you can take that as data set and plot it. So you create an initial blank plot with the frame num on the x-axis and the mean intensity on the y-axis. So frame num is a change over time. We can add g_on_point there with size equals 0.1 and alpha just to see the changes. So what you can see there is that there's certain values, there's just a handful of values that are very low that can distort this whole picture. And then we can jitter them maybe to make it more easy to read. So, and then we can add on the smoother as well. So you see the more jitter there, it's easier to read. Smoother to follow them over time. And then we add a xlab, the frame, and then the ylab is the mean intensity. So there you see the frame and just change the y-axis labels. So you can see at stage 12 to 15, there's a bit of variation there. So let's explore that more. What we're going to do is count the number of spots, the number of spots by frame, and store the resulting column called NB. What we're going to do is group the spots by frame and count them using the function n. So taking our fly spots, grouping them by frame, and summarizing with this function, we're assigning NB to be equal to n. So if we look at NB nuclei now, you see there we just have the frames and NB is in there. So you can view that whole column on the line 2388. And you see there we have NB going from high to low. Okay, so let's now take this data and do standard analysis such as we might implement with software like Fiji or ImageJ. We're going to look at visualization of these different tracks using these packages to allow 3 and 4D visualization of these different spots. So we're going to use this XML file looking at the division time lapse over time containing our spots and tracks. So what we're going to call it here is division time lapse trackmate XML file. So we're going to xml to list, and this will create 2 items in the file XML entry. So let's look at that there. We have quite a lot of items there for each of the spot because it's a list. So what we're using are these 2 functions, spots as data frame and tracks as data frame, to take this file XML and extract the spots data frame and tracks data frame from these. So then we can look at tracks and spots in more detail next. So these steps may take a while, so let's just check that they work. So we're looking at the head of the spots. So we have our table there just containing 21 columns and 6 entries. And then the tracks again, we do the same just to check it worked. So we have our spot source ID, our spot target, our link cost, edge time, and the edge location as well. So now what we want to do is examine the fluorescence variation prior to division to spot false positive divisions. So this is kind of at the early stages of this time lapse. So we're looking at converting the mean intensity data to numeric. So that's as numeric. So we're going to call this spots_df. And then we're kind of calculate the number of spots per frame. So we're going to use a summarized function. We're going to be setting NB equals N. And we're going to store that in NB nuclei like we did before. So we're checking that it worked. So we see that now with down below, we have a table containing the frame and then the NB values. We can create a temporary data frame called spots_df. We're using left join to link spots_df and NB nuclei. So we're linking them by frame. So if we look at NB nuclei, $frame, and then if we look at spots_df, $frame as well, you can see that they contain spots. If we look at more, frame has lots of them in there for DF, different values. As you can see, they're sorted there. So if we do this, we can check the structure of this linkage. So it now contains 18,000 entries across 22 columns. So we have linked in our NB value there for the averages where they're linked into the spots_df data frame. So what we can do is use this count spot function in Mammuter to do the same calculation as above. So we'll take the spots_df and the frame column to link them together, and we get the same thing. We get 18,000 columns across 18,000 rows across 22 columns. So now we can look at the 4D visualization of the mean fluorescence intensities. We're going to use the plotly spots all from the package CellViz 3D that takes in our data frame, the X and Y positions and Z position, the time, the numbers, and the mean intensity is the color. So if we plot this 3D visualization, we'll see a plot on the right-hand side that we can explore more fully. So we just make this a bit wider so we can see it properly. So these things take a while to produce because they're complex images. So there we have it on our right. So you see there we have our graph. We can move it around. So we have the y-axis there in front. And then we have the x. Is this x? Yeah, x there. And then we look at the depth as the z-axis as well. And then we have the color as well. So we look at this changing over time. So you can't see much differences there. If we look here in the middle, we'll see a bit more of the cells reorganizing there over time. So you can see that there's definitely changes going on. And we just have to kind of interpret them in the right way. So we see the spots on the board have a lower fluorescence than the ones in the embryo. You can sort of see that as a chart at the end there. The ones at the edge have a lower intensity, suggesting that they're dividing less. So we can filter out the ones with the lower values and see what happens. So we're going to filter that to form the spots DF filtered, and then plot our graph again and see what changes we get for the same sort of graph. So now we can see a slightly different plot where the range of values is more restricted. If we look at it over time, yeah, you can see that there are definitely big changes there. The numbers of cells increases dramatically, and you see the intensity is stronger in the middle, and the cells kind of bundle up together there. There's really significant movement, and the intensities at the edges are still lower. So let's look at the spots that are about to divide. So what we're going to look at is the tracks DF, that is the info of the tracks. It is the ID of the source spot and the target. If the cell is dividing, it will have two targets. If it has zero targets, then the cell dies. If it's one target, then it just is retained. What we're going to use is use n to count the number of each source to detect cells that are about to divide. And then we use left join to put this in a spots.df data frame. So saying dividing cell is going to be the tracks.df, where they're organized by the spot source ID and the status there. So we can check the dividing cell setup. So we have 16,000 to 16.7 thousand such cells. And then we can left join that with spots.df by ID. Put the spot source ID to create add this information into this data frame. So we got 18,000 entries again. Now we're going to look at the 4D visualization using plotly spots all. We're going to count spots for the spots.df, which we did before, and plot that. And focus on cells that have two targets. So that's working now. So the plot is rendering. We can look at that now. So we can see it from different angles. If you play, you see the number of cells increasing, and then we see a lot of change. We have key cells and key stages of where the intensity rapidly changes. We see around now at 730, high fluorescence and high rates of cell division that are different from the other parts. What we can do is compare the difference of the intensities before and after cell division to find false positive ones. So we get the mean. We're going to get the difference of the mean intensity before versus after division, and then we're going to look at the difference of the mean intensity between consecutive time points, and we're going to group these differences according to the cell's fates. So looking at spots.df, we're selecting the ID and the mean intensity, filtering those for the lower, filtering out those with the lower intensity, and checking that those ones that are stable are about 14.6 thousand. And then what we're going to do is create a tracks.df target source data frame containing tracks.df, where we're left joining on the small valid spots for their spot source ID, where we're renaming the mean intensity source as the name for the mean intensity. Same for the next part for the next part. And then we're grouping them by spot source ID, or summarizing the division status numerically, where the mean source is equal to the mean intensity score, and the mean target is the mean intensity target. And then we're going to mutate that so the difference is computed as the difference between the mean target and the mean source. And we're going to look at the structure of this output at the end. So if we look at the structure, we have 16.7 thousand entries, where we have the spot source ID, the division status, the mean source, and the mean target, and the difference between them. It's the mean fluorescence before and after. So what we can do then is plot the difference of the mean fluorescence intensity for non-dividing cells versus the dividing ones between time points. So we're looking at tracks.df target source, that plot, and we're looking at the differences first of all. So we've got this empty plot at the start, and we can add a histogram onto that with the histogram of the bins at set to bin 80. And we're going to add a line onto that to set the vertical line where it's 0, just for visibility. And we can fuss it around that the division status from our table above, where we have div status. And then we can set the scales to be free Y, one column for the two plots, and add the X label that we have the difference in the mean fluorescence intensity. So two plots, top and bottom. These are the static ones on top where there's no change on average, and the lower ones where we do see a change. So here you can see that there is a change. The source and the target show a difference. So they're the ones that are dividing. So what we can do next then is locate the spots with a positive difference in mean intensity which are false positives. So what we're going to do is look at the difference to spots DF with left join. So we're going to look at the different target source. We're going to link them by the spot source ID and the division status. We take that to have the difference of the division status where it's less than 2 to look at the difference. So let's look at that first of all, and then assess that using count spots to get our entries. So you can see we have 18,000 entries. And next, what we're doing is using this function again to take that data frame, plot the X, Y, Z, and look at the changes over time for that distribution we've just made. So there we can see it. We have our plot there. So we can see now, if we look at our plot changing over time, we have the difference shown here. So we look at it over time. We can see that there are different key points where there are differences in changes in intensity. So we can see here at a 130, there's a big difference where they're all changed slightly, and then that decreases. And then again at 3 minutes, you get it again. And then at 5:30, we get it again. And then a slight one at 7:30, but that's it. Okay, so that kind of shows how we can kind of look at 3D visualizations of cell dividing over time and look at ones where we have false positive cell divisions at the start before the main cell division later. So that's the end of this demonstration video.